Welcome to my YouTube channel, Dhanesh here. This is the fourth video on gradient descent. See, we covered many aspects related to gradient descent. What is gradient? What is slope? Gradient or slope are the same terms only in terms of mathematics and statistics. We covered those aspects. We covered some idea on calculus. We covered partial differentiation, some concepts of partial differentiation, and we discussed maxima and minima. We discussed cost function, back propagation, learning rate, many aspects. Some important aspects we discussed are cost function, back propagation in the previous video related to gradient descent, back propagation, learning rate. So all these aspects we covered. This is denoted by alpha, learning rate or alpha. See, these are all, in terms of machine learning or AI, these terms are very important. And another term I can tell you, it is mean square error. See, this term also we discussed. What is mean square? Sometimes root mean square also we will use. See, what is mean square error? See, all these aspects are important for we use it across AI, machine learning, neural networks, everywhere. Please watch the previous videos related to gradient descent. This is the fourth video on gradient descent. Let me talk about, to begin, we will continue with the cost function. This is the term cost function. This is related to error. See, cost function denotes error. And I derived a formula in the last video. It is 1 by n sigma I is equal to 1 to n y dash minus y the whole square. Why we are using this square? This n is for the mean. Dividing with n means it's mean. Why we are using this square? We discussed in the last video, because when this y dash is the predicted value. Y is the actual value. So when you subtract, you can get positive and negative values. So when you add it, they can cancel each other, and you will get, you won't get the accurate result. That's why we are squaring it. So the square of a negative number is positive. The square of a positive number is also positive. So that's the concept we explained clearly in the last video. Please go through that. And y dash, that also we discussed in the last video. Y dash you will substitute as, so your equation becomes 1 by n sigma I is equal to 1 to n, y dash is mx plus c, the equation of a line, minus y the whole square. So this is the important informations related to cost function. We covered all those aspects in the previous videos. So I am coming to now I am getting into gradient descent. It is an iterative. So that's also we discussed. It is an iterative optimization algorithm. Gradient descent is an iterative optimization algorithm to find the minimum of cost function. This is gradient descent. we discussed in the previous videos. Gradient descent is an iterative optimization algorithm to find the minimum of a cost function. See, all these aspects we cleared in depth. This is a repetitive process. To find out the minimum, we can use calculus, but there are some limitations. To find out the maxima and minima of a function, you can use calculus, but there are some limitations. That's why we are using this gradient descent. So we will get into the details more clearly, then you will get an idea about this. Now, gradient descent, see, even we discussed back propagation, learning rate, see, all those aspects we discussed. To get into the more aspects of gradient descent, I can tell you one important point. I told you how to find out the minimum. See, gradient descent is using to find out the minimum of a cost function. Why we want to minimize cost function? Because we want to minimize error. Cost function denotes error. If the cost function is minimum, means error is minimum. Okay. So to minimize a function, we have calculus. The first derivative test, the second derivative test. It's there. Why we are not using calculus? It's somewhat simple answer. Why we are not using it? The reason is, for example, if you have a function like this, f of x is equal to e raised to some complex function minus x raised to p, then you have some constants alpha, then you have some another values like x raised to m, the whole divided by, you have again beta, again x raised to cos x, or you can write it as x raised to cos, then again e raised to x. This is a complex function. If you see, you can see this function is somewhat complex, and you can apply the product rule or quotient rule of differentiation to find out f dash x. Then you will get f dash x. Then the challenge here is you need to equate f dash x to 0 and then solve for x. To find out the solution, it would be a complex process when the function is complex. You understood? For finding out the minima, you can watch the previous videos. The f dash x, you will equate to 0 and then you solve for x. But solving this, f dash x also will be a complex form. Then solving those equations is really tough. That's why we are coming to this gradient descent approach. So you understood why we are getting into gradient descent approach. So now I will get into that process. What exactly that iterative optimization process? See, here we use optimization. So for optimizing the bias and the weight, see, I clearly mentioned in the equation y is equal to mx plus c. M is the slope and c is the y-intercept. In machine learning and neural networks, this m is known as the weight of the network and c is known as the bias. So these terms again really important. We discussed in the last video as well. So in a neural network or in a machine learning algorithm, this m stands for weight and c stands for bias, and x is the input and y is the output. This x is the input. So all these things you can understand, and y is the output. This is another important thing you need to understand. So optimization, iterative means you can understand gradient descent. It's an iterative process, repetitive process. Optimizing this weight and bias. So that's what here we are going to do. So now you understood what is weight and bias. These aspects we discussed in the last video as well. So now I am getting into another function, f of x is equal to x square minus 2x plus 2. This is a function, you are having it. If you plot the graph of this function, see, you can easily understand from here how do you find out the minimum. You will by calculus. First I am telling you the calculus method, then we will get into the gradient descent approach. See, you will calculate f dash x, then you will equate to 0, then you will find out the value of x. That value of x will be the maximum. Sorry, that value of x will be the minimum. It can be maxima as well. To if the function is having both maxima and minima, then we will get into the second order derivative test to find out which is maxima and which is minimum. So that we discussed in the previous videos. So I am not getting into those details. See, the simple approach, we will calculate f dash x and equate to 0. Then the corresponding value of x can give you the minimum of that function. Let us assume that this is the cost function. Okay, so f dash x, you know the derivative. So the simple rule we are using everywhere here for the differentiation. I have given a simple introduction. Those who are facing problem with maths, you can use, this is the formula we are using. Differentiation means it is the splitting process. Integration means again we are summing all those minute details. That is integration, and this is the branch of mathematics known as calculus, introduced by Isaac Newton and Leibniz. So you know all those aspects we discussed. D by dx of x raised to n is n x raised to n minus 1. The same here, instead of n here is 2. Then it would be 2 x raised to 2 minus 1, that is 1, that is 2x minus 2. The same thing, x raised to 1, 1x raised to 1 minus 1, that is 1x is x. 1x raised to 1 minus 1, x raised to 0, x raised to 0, any quantity raised to 0 is 1. So the derivative is this, 2 into x minus 2. So what we will do, see all these aspects, the differentiation, if you are not good at mathematics, you can learn these formulas and try to do it, because maths and statistics is an essential part of, but you don't need to worry about that. You can slowly you can learn these aspects. It's not very difficult. So you can get it like 2x minus 2. Then we will equate this f dash x to 0. Then you will find out the value of x. So here you can 2, it is common, 2 into x minus 1 equal to 0. That means x is equal to 1. This is the point where you will get the minimum, and x is equal to 1, this function will be minimum. So this is the calculus approach. Then what is the gradient? See, even if you plot this graph, you will get like this only. If you plot this graph, you will get like this. This minima should be at 1. This is 0, this is 1, this is 2, like this. Here it is minus 1, like this it will go. The plot of the graph, if you without all these aspects, if you are plotting this graph, this function, you will get it something like this. So you understood that x is equal to 1 is the minimum for this function. So how do you apply the gradient descent? I am assuming all these aspects. See, here x is equal to 1 is the minimum. Now from calculus approach and by plotting the graph, you got it. So again I discussed you previously why we are using this gradient descent approach. Why can't we use this calculus approach? Sometimes the function should be very complex. I have written one such function. The f dash x will be more complex. Then solving that function is very difficult. For x, solving for x it is very difficult. Now we will get into the gradient descent approach. So by this approach, it is an iterative process. I told you, it is a repetitive process. We will assume, let us assume that x equal to 3 is the minimum. This is the minimum. It's wrong. We don't know. We are in a program. We use a Python or a Java or R program. You have in machine learning, we mainly use the programming languages Python, R and Java. You know this. These are all the important programming languages we use in machine learning. See, that with the help of a program we do this. See, let x is equal to 3 and we are assuming this x as the minimum and we are doing a repetitive process to find out whether this is correct. We know this is wrong. Now, then if it is minimum, the f dash 3 must be 0. So we will calculate f dash x. The key point is, if this is correct, then what would be a 0? F dash 3 must be 0. You are getting my point? So f dash x must be 0. See f dash 3 here. See, because we have taken, that's what we discussed previously. So f dash x will be 2x minus 2. Then f dash 3 must be 0. So f dash, the reverse process. By how do we find out the minimum? By using calculus method, we calculated f dash x and then we equate it to 0. Right? Then the reverse approach. If this is minimum, then f dash 3 must be 0. That means 2 into 3 minus 2, that is 6 minus 2 equal to 4. This is wrong. So this is not a minimum, we understood. So f dash 3 is not a minimum and it is a positive value. That means, see, again we have to go back. If you got a negative value here, you need to go forward. You are getting it? So you put x is equal to 3. So these logics we need to implement in a Python program. So that to find out the minimum. So again we need to go back. See, we will put, let x is equal to 2. Let us assume that, see, in a program you need to do thousands or 10,000 iterations to get the more precise answer. Here one is a whole number. One is a whole number. Sometimes the minimum won't be a whole, it is a decimal value. See, you can, so there we need to use the multiple iterations, 1,000 or 10,000 iterations, even more, to get into the exact minimum of a complex function. So here we got into so 3 is not, then we will put x is equal to 2. Then we will calculate f dash 2. F dash 2 we calculated. Then what would be the answer? Here again 2 into 2. You will get 2 into 2. That is 2 into 2 minus that. The answer is for 2. Then it is again coming down. That means we are approaching towards the minimum, right? So it is not the result. Then we will substitute x is equal to 1. So again, next, see, even this is not 0. Then let us assume that x is equal to 1. So here I am, manually when I am doing, it is, we are doing it in 2-3 steps. See, then let us assume that if I am putting x is equal to minus 1, see, then I can calculate this. then what would be the answer? So I am going backward. So came up to 2. Then let me see that if I am putting x is equal to -1, then 2 into -1. Sorry, 2 into x. So here it would be -1. So it would be -2. -2 means it is -4. That means I need to go forward. That is -1 is not the minimum. So let me put +1. This is an iterative process. So I will put x is equal to 1. Then here it would be 1. Then 2 into 1, 2 minus 2. Then it is it is 0. Here it is f dash 1. F dash 1 equal to 0. That means x is equal to 1 is the minimum of this function. This is a repetitive process. We are choosing a wrong value for x, then we need to go forward or backward. If f dash x we are getting positive, our aim is to get it as 0. If it is positive, we need to come backward. If it is negative, we need to go forward with value of x. For example, when you substitute x is equal to 2, at that time f dash x is positive means next time you will check x is equal to 1. Again, if you are getting that positive, next you will check it with x is equal to 0. Again it is positive, then x is equal to -1, -2, like that you will go. So for example, when you in another case, when you substitute x is equal to 2, at that time f dash 2 is negative, then you will try with x is equal to 3, 4, 5 in the forward direction. This is what I am trying to say. See, now based on this, how we can approach mathematically these things, how we can put it means, see the previous value 1, this we can write it as mathematically the value of x, we are taking it as I plus 1, x I plus 1, generally one value of I plus 1 x will be xi, right? We are coming back. In the case of a minimum, we will come back, right? First we tried with a 3, then if it is positive, we need to subtract xi minus alpha. This alpha is known as the learning rate. So this is the important equation for the gradient descent, alpha into f dash of xi. Some values we need to subtract. So that value we are taking it as in our control alpha of f dash xi. So the value alpha in the last, so this is the, I will explain this equation more clearly. This is the important equation. So here when it is if it is minima, here minus, if it is for maxima, for example, if you get f dash x as negative, you will put plus here. So it is plus or minus. F dash x, you got it as positive, you will subtract it. So what is alpha here? I already discussed. Alpha is the learning rate. Alpha we call it as the learning rate. Its value varies between, alpha is learning rate. In the previous video we covered, its value changes from 0 to 1. If alpha is very less means the machine learning model progresses, it's training very slowly, that's what. And if it is alpha is very high, it is near to 1 means we will get undesirable results in the cost function. So that's the variation of alpha. Its minimum value is 0, maximum value is 1. F dash x, the derivative of x function, you call it as f dash x. Another approach is dy by dx. dy by dx and f f dash x are same only. Those who do not have idea about mathematics, you need to understand the first derivative f dash x and dy by dx are same. The second derivative we call it as d square y by dx square or f double dash x. Second derivative is known as d square y by dx square is f double dash x. Both are same. See, this is the equation. X I plus 1 is equal to xi minus alpha into f dash xi. So this is the equation for gradient descent. This equation only we need to implement in a program. See, now you need to understand, see how we will come up with these equations. More, see, this equation we understood. So I am getting into the optimization of weight and biases. So we are going to get into those details. So you can see it here. You will get more clarity on that. How we can use this equation to optimize the weight and bias in terms of cost function. So this is our equation. X I plus 1 is equal to, this is the equation, xi minus alpha into f dash xi. This is the equation for the gradient descent by by analyzing the calculus and other methods. We put some wrong value and this is the conclusion we made for gradient descent. Now the equation for gradient descent. But the cost function, it is denoted by the letter J, cost function. It depends on the weight. It is m and the bias m. So it is dependent on two functions. It is equal to 1 by n sigma I is equal to 1 to n. You have this equation. You have this equation, that is y dash minus error the whole square. See, y dash minus y the whole square. Here y dash is the predicted value and y is the actual value. Even we substitute like this, 1 by n sigma I is equal to 1 to n. Y dash is mx plus b minus y the whole square. This is the equation for cost function j of mb. So this also Now what I am doing is this equation I am considering the second equation. Here what is y dash? It is mx plus b. I am writing it here. mx plus b minus y the whole square. Now I am finding out, here we have only one variable x, but actually we have dependencies on two variables. So we discussed about, partial derivatives. When I discussed about this equation, I consider f as a function of x only, but the function can be this. To understand more clearly, please watch the previous videos of gradient descent. This is the fourth video. So there we discussed about partial derivatives. See, partial derivatives when comes into picture means when a variable depends on two variables, x and y. Here our cost function depends on two variables, weight and bias. So here whatever we discussed in the previous case, it was fx. That function was fx is equal to x square minus 2x plus 1. So it depends only on x. Here instead of x, we have two variables m and b, two weight and bias. Okay, so in the partial derivatives we have taken x and y, and I told you, I discussed about the calculus approach of partial derivatives. So here since we have two variables, you can write this you need to understand this mx plus b, the entire term, if you take it is error only. Mx plus b minus y. This denotes error. So first I am differentiating with respect to j with respect to m. So the point here is in terms of partial derivatives. When you differentiate the cost function with respect to m, b will be a constant. The derivative of a constant is 0. We already discussed the derivative of a constant is 0. So this, the derivative, we can take it as, here you can take it as, this is again the rule, x raised to n d by dx of x raised to n is equal to n x raised to n minus 1. So it would be 1 by n, this is a constant, then 2 into error. See, this term I am taking it as 2 into error because this is the actual, predicted minus actual. 2 into error, n x raised to n minus 1, 2 minus 1, it is error only. Then we need to consider, we are differentiating with respect to m. Here, then x becomes a constant. Then into, you need to write, see what is the derivative of 5x with respect to x? It is 5. When it is with respect to x. What is the derivative of 6x with respect to x? It is 6. In the same way, here m is the variable and x, b, y, everything is constant. So, what is the derivative of mx? M is the variable, x is constant. Everywhere you see x as variable. So, into x. Into x. Here I am neglecting this 1 by n, even 2 as well. You can neglect it. See, you can take it as it is error into, see, dou j by dou m should be, you can, because these terms, why I am neglecting it is, you can, you can incorporate with the learning rate. It is another constant alpha. But for the time being, you learn it as 1 by n into 2 into error into x. This is what you got it for, dou j by dou m. In the same way, when you calculate dou j, this cost function, divided by dou b, at that time m is a constant. Again, you will get 1 by n. Then here you will get 2 also there. 2 also there. This we will neglect it later. Into 2 into error n x raised to n minus 1. This formula 2 into error. But we are differentiating to b. All these terms are constants here. B. What is the derivative of x? 1. What is the derivative of b? Into 1. So you will get 1 by n, 2 into error. So that's what you got it. So you got dou j by dou m as 1 by n, 2 into x, and 1 by n, 2 into error into 1. See, again, since we are substituting for this f dash x only here. This dou j by dou m and dou j by dou b. This is the derivative, partial derivative. So this equation I am not writing here. Now it is raising. See, this we combine. See here, this when we talk about instead of xi plus 1, I will take our variables, the weight and bias. M of, it is, you can take it as I plus 1 should be mi minus alpha. This is a constant. So this 1 by 2 into n, 1 by n into 2 will be adjusted with alpha, and we will write it as, instead of this, error into x. This is the important equation, error into x. This is into error into x. This is the most important equation for writing the gradient descent program in Python or Java. So this is the way you are getting that equation. This is for the weight. Now if I am writing the bias equation, again I can write it as, when I am writing the bias equation for B, that is another variable, weight and bias, the optimization only we are discussing here. B of I plus 1 is equal to Bi minus alpha. This, again 1 by n into 2 will be adjusted with alpha minus alpha into error. Here there is no x. So these are all the most important equations for weight and bias. So this is the general equation for gradient descent. All these equations, these three equations are really important. So this is about the concept of gradient descent. So these three equations. It is the most important equations of gradient descent. So this is the general equation. When two variables comes for our gradient descent, it depends on the weight and the bias. So for that, this is the equation we derived it. Now, you need to understand, when we consider these approaches about this cost function, we consider only 3 or 4 rows of data, right? It is a very simple things only we discuss. But in real-time projects, when you discuss about real-time projects, you can have millions or billions or trillions of rows and columns. The data will be very huge. At that time, you need to understand. So these iteration, see how this is. We will assume like x1 value, then again next value, again next value. This process, if we are doing it for trillions of rows of data, it's really complex. Then what we will do is we have to select one random data from the entire data set. See, we will select one data, and for that we will do this process. So such approach we will call it as the stochastic gradient descent. Very important. It is known as stochastic gradient descent. Stochastic gradient descent. So you know it. This is the concept you understood now, because in real time projects you have millions and billions of data. See, at that time what you will do is you will take we use only one sample from the data, and we will do this process. For one sample we will do this process, and that approach we call it as stochastic gradient descent. Then you can understand it will be accurate. The accuracy will be less when it compared to the stochastic gradient descent. At the same time, the speed will be very high because we are taking only one sample of data. Alright? But if we are taking all the samples, then it is known as the batch. The gradient descent, we call it as the batch gradient descent or regular gradient descent or batch. So that is another term you need to understand, that we call it as this is the first thing I already covered, stochastic gradient descent. The next is the regular gradient descent. Regular gradient descent, it is also known as the batch, because the entire sample of data we are considering, it is known as the batch. So here we are using all the n samples. So in stochastic gradient descent, we are using only one sample. Here we are using all the n samples of data. If there are trillions of data, we will use all trillions. So So that is the regular gradient descent. And there is another approach. We will take, not all and even not one, in between some values we will take. Such process we call it as the mini batch gradient descent. Mini batch gradient descent. Here we take m samples, and this m is greater than m, and it is in between less than m. So this m is between 1 and n. That is known as mini batch. This mini batch will be more accurate than the stochastic gradient descent and less accurate than the batch gradient descent. So the most accurate is the batch. After that, mini batch. After that, stochastic. The fastest is stochastic. After that, mini batch, and the slowest one will be the regular gradient descent. So this is the fourth video we completed related to gradient descent. We covered in depth. See, this algorithm we covered in depth. In the next video, we are going to write a Python program to implement this algorithm. So thanks for watching.